In this section, we're going to talk about the ideas behind simple linear regression. So first off, let's just mention what regression is. Regression is basically the idea of prediction. It is predicting one variable based on another variable, or technically it can be multiple variables within your X or your Y. You can actually predict multiple variables based on multiple variables. But for our purpose, we're going to keep it simple, and we're basically going to look at just a simple linear case where we're predicting one variable based on another variable using a linear model. So in order to use linear regression, the first thing you have to do is you have to establish a relationship between your variables, and then once you establish that relationship, then you can lots of times create a model that will predict one variable based on the other. So we need to start with the idea of a relationship. So in statistics, when we're looking at a relationship, we're talking about whether or not two variables are correlated. So correlation is simply just we say variables are correlated when there is a relationship, a mathematical relationship between the two variables. To identify correlation, we really look at two things. When we're looking at two quantitative variables, we look at a scatter plot, which is just a graphical display of our two variables, and then we look at an R value, which is a measure of how strong the relationship is along with the direction of that relationship. When we do identify a strong linear correlation, that's when we're able to use this idea of regression, and we will be able to, using a linear model, be able to predict Y based on X. Of course, there's going to be some error involved in this process because whenever we do statistics, it's not like we're going to have a perfect relationship. This is not like an algebra class where you have this perfect function, and if you know what X is, there's exactly one Y. We also have error to deal with in here because there's going to be variability across individuals. So we always have this variability across individuals that we have to deal with in statistics beyond just the basics of the model. We know there's going to be error in this process. So let's start with the idea of looking at some scatter plots and make sure we can identify the correlation within a graph. So we will focus on the linear case. That's what the graphs are going to look like. Anything that's not linear, we will just say there's a non-linear correlation. But we're going to start really with a focus on the particulars of what we look for in a linear relationship. So this is our first example. This example is not really necessarily realistic in terms of what you would get whenever you collect data, because this is one of those scenarios where all the points are exactly on a line. So this is more of a reference point more than anything in terms of what we do in statistics. It's a good reference point for how strong a relationship can get. The strongest a relationship can ever be is when all the points are exactly on a line. If you're talking about a linear relationship, the strongest a linear relationship can be is if all the points are exactly on a line. Now, in reality, when you collect data, you're always going to have this variability across individuals, so you're never going to get this perfect kind of relationship. But if you would see a graph like this, it is perfect because all the points are exactly on a line. This line has a positive slope, so it's positive, and of course it's linear. So we would identify this as a perfect positive linear correlation. And like I said, the only time we say perfect is if all the points are exactly on a given function, in our case a linear function. So you would only use that term perfect if all the points are perfectly on a line. In reality, that's really never going to happen, but this is kind of the ideal scenario where we have this perfect relationship. The positive, of course, comes from the fact that this line, if we draw a line through all these points, would have a positive slope, and then we want to make sure we identify it as linear correlation. So you should exactly say what I have there, perfect positive linear correlation. If we look at this second graph, almost exactly the same. The only difference is it has a negative slope. So of course, we still have that perfect relationship, negative slope. So here we would want to say perfect negative linear correlation. This next graph is a little more of a realistic graph. Notice all the points are not in any kind of perfect relationship, but there definitely is a pattern. You can see as our X variable increases, our Y variable also increases, and it does increase in a linear pattern. Now, there's no perfect line that goes through all those points. That's not what we're looking for here. We're looking for an overall pattern. But if I draw a function through kind of the middle of those points, you will see that it would be basically a line, and that line would have a positive slope. Now, all the points would not be exactly on the line. You would have some variability there away from the line, of course, but this would have a positive slope, and it does follow a linear pattern. So this is what you're looking for whenever we say positive linear correlation. This next one is very similar. The only difference is, of course, it has a negative slope. Still, these points follow that basic linear pattern. So here we would say this is a negative linear correlation. If you get a graph that looks like this, or has some kind of pattern that is not linear, because obviously there's a pattern here, right? From left to right, you can see as x increases, this graph starts to decrease, but then it gets to a minimum down there, and then it starts to increase again. This looks kind of like a quadratic function or a parabola. So you could actually probably model this with some other kind of function other than a linear model. But I won't make you go back and remember every kind of function you've ever dealt with in your mathematical life. So anytime you have a pattern like this, that's a relationship that is not linear, then you can simply just say there is a correlation. It's of a nonlinear type. Do be careful with your wording here. Make sure you say nonlinear correlation, because that does imply there is a correlation and it's of a nonlinear type. You don't just want to say no linear correlation, because no linear correlation, of course, means there's no linear correlation, but it doesn't necessarily mean there is some other kind of correlation. So it's important your terminology here. We're just going to use this idea of nonlinear correlation when we have a pattern that is not linear. So that's what you should identify in these kinds of cases. If you wanted to say this is a quadratic relationship, I'm fine with that as well. But really, for these, all that you need to do is identify there is a correlation. It's of a nonlinear type. So you just want to say nonlinear correlation there. It is possible, of course, to have a graph that really has no pattern. The points are just kind of everywhere. So if you get a graph like this, of course, there is no relationship between x and y here, so there is no correlation. So basically, if there's no pattern, there is no relationship or no correlation between these two variables. So that is our first way we look at correlation, or the relationship between two variables, is we look at it graphically through this idea of a scatter plot. The second way is we look at an R value. So let me first just show you the formula for R. The basic formula for R is based on some different sum of squareds. So we basically take the sum of the xy's and divide that by the square root of sum of squared x times the sum of squared y. So that's what those stand for. The numerator is sum of the xy's. The denominator has two sum of squareds in it. The first one, SSX, stands for sum of squared x's, and the SSY stands for sum of squared y. Of course, x is our x variable, y is our y variable. And you can see what each one of these represents. The sum of the squared x's, this is a very common quantity in statistics. That SSX, you've seen that before actually, is the sum of x minus x bar squared. If you remember when we talked about variance, that is nothing more than the numerator of your variance formula. The sum of squared x's, if you go back and look, is how we identified the numerator of our variance formula. The SSY is exactly the same thing. It would also be the numerator of your variance formula, just for your y variable instead of x. The SXY, you'll notice, instead of having a squared, what we have is we have one term that includes x, and we have another term that includes y. So we have the x minus x bar and the y minus y bar multiplied together instead of having two of the same term, so it's not squared. So what that actually is if you divide that by n minus 1, you actually get what's called covariance. So all of these are really variance terms. If you divide each one of these by n minus 1, you get the variance of x, the variance of y, and then what we call the covariance. So the covariance measures the variability in the relationship between x and y. And then, of course, the sum of squared x's is the numerator, or when you divide it by n minus 1, measures the variability in x. SSY measures the variability in y. So these are basically three different variance components that we use in order to calculate this R value. So this R value is going to tell you a couple things. This R value is going to tell you both the strength and the direction of the linear relationship. So the direction is pretty straightforward. The direction is simply, is the relationship positive or negative? That's what we mean when we say direction. The nice thing is if your R value is positive, that means your slope is positive. It basically means that the relationship is a positive relationship. It means there's a positive linear correlation. If the R value is negative, it means there's a negative linear correlation. So direction is really simple with R. You just look at the sign and it tells you the direction. The strength is a little more messy. The strength tells you basically how close the points are to the line. So we've already said that a perfect relationship is when all the points are exactly on a line. That's the strongest relationship you can have. So the absolute value of R, the quantity itself, actually tells you how close the points are to the line. And the closer the points are to the line, the stronger the relationship is. That's how we talk about this. We say that when the points are closer to the line, we have a stronger relationship. Because when you start getting points far away from the line, the relationship isn't very strong because the line's not going to predict it very well. So a few things in terms of R. Let me give you some facts and then I'll talk you through the formula a little bit. The R value is actually always between -1 and 1. So if you ever calculate an R value and it's not between -1 and 1, you know you made a mistake somewhere. You have to figure out that mistake. All R values are between -1 and 1, and this is forced by the makeup of the formula. And like I said, I'll talk about that here in a minute. So the strongest relationship you can have is when the absolute value of R is equal to 1. So if the R value equals +1, that means the direction is positive. It also means you have the strongest positive relationship possible. So the only way R will equal 1 is if all the points are exactly on a line with a positive slope, meaning that we have perfect positive linear correlation. And that's another reason why this is a good reference point. This is the strongest relationship you can have in the positive direction, and when R equals 1, that's the only way that can happen. If R equals -1, of course, it's the same deal other than the slope is negative. It's the absolute value of R that's important to keep in mind that tells you the strength. This is also a perfect relationship, as strong as you can get, only now the sign of R is negative, which means it's a perfect negative linear correlation. If R equals 0, then that means there is no linear correlation. Now, it doesn't necessarily mean there's not some other kind of relationship. It is possible to have another kind of relationship and still get an R of 0, but it means there is not a linear correlation between the two variables. Another important value to keep in mind is, well, we know R is never really going to be 0, 1, or -1. So we want, obviously, R to not be close to 0 because that means there's not much of a relationship at all. And if it's close to 0, there basically is no linear correlation. But what we want it to be is either close to 1 or -1, depending on if the sign is, or depending on if the relationship is positive or negative. So then, of course, the question becomes, well, we want to be able to say that we have a strong relationship. We want to be able to say these things are correlated and the strength is strong. We want to say the relationship is strong. So in order to be able to say the relationship is strong, we need some kind of general rule. I do want you to know that there is no perfect general rule for what's strong, but this is the general rule that I will give you, and it's the one I would like you to use. If the absolute value of R is at least 0.75, then that's when we're going to say the relationship is strong. So if you get an R value of 0.9, that's a strong positive linear correlation. If you get a R value of -0.8, that is a strong negative linear correlation. So we'll use that term strong when we get an absolute value of R bigger than 0.75. I do want you to keep in mind that there's not a huge difference between 0.74 and 0.75. It's not like all of a sudden at 0.75 the points get closer to the line. That's not the way it works. As R gets larger in terms of absolute value, basically the points are gradually getting closer to the line. So there's no perfect point at which for R that the points are just now close to the line. But we do need some kind of general rule, and this is a good general rule. You would always want to look at your graph and at your R value. I will tell you, when I ask most questions I ask, I either give you an R value that's bigger than 0.75, so it's obviously strong, or I give you a low R value, so it's obviously not very good. If you have something that's maybe 0.5, sometimes people will call that the strength is of a moderate nature. So sometimes you'll hear people say there's the correlation there is moderate. I'm not so worried about that category of moderate. Anything that's not 0.75 is not going to be strong enough to use linear regression. It's not going to be strong enough to predict, which is really a big part of why we use this R value and why we look for a strong relationship. So those are some important values to be able to recognize and understand what those values represent. Let me get back to the formula so I can just talk a little bit about why these values represent what they do. And I'll try not to bore you too much with the details of the formula, but let me just give you a feel for what the formula is doing here. So the formula is a mix of variance components, like we just said. It's basically deals with the variance of x, the variance of y, and the covariance. If you actually just take the covariance divided by the square root of the variance of x times the variance of y, you'll get the exact same formula. Basically, all the denominators just cancel out here. So this is really just a mix of variance formulas that's put together in the proper way so that we can measure the strength and where the variability is actually coming from. So the numerator of the R formula is the covariance. So it measures how these two variables vary together. The denominator has the variance of x and y separate, and then we combine them in such a way that it basically represents the total amount of variability we have in our two variables x and y. So in terms of strength, that is important, because when you look at the strength of this relationship, the numerator of the R formula basically says how much variability is accounted for by the relationship. The denominator basically says how much total variability is there. So when will that be equal to 1? Well, it'll only be equal to 1 if the numerator and denominator are equal. So the only way for that to be the case is if out of all the variability, which is the denominator, if all of it's accounted for by the relationship, then these two quantities will be equal, because the numerator is how much of the variability is accounted for by the relationship. If all of the variability is accounted for by the relationship, then that numerator is going to be equal to the denominator, which is the total amount of variability. This is also why your R value can never be bigger than 1. You cannot have more variability accounted for by a relationship than you have in the variables together. The most variability that can ever be accounted for in a relationship is however much total variability you have in the variables individually. So if this thing is 1, that means it's a perfect relationship. That's as strong as possible. And basically, the way this R formula works is the numerator is how much of the variability is accounted for by the relationship. So the more variability accounted for by the relationship, the higher this value gets and the closer to 1 it gets, because the closer that value gets to the value of the denominator. So when this value gets high, it indicates strong relationships. High in terms of absolute value. The other part of this equation that formula that's important is the direction. And the direction is actually pretty straightforward here, because if you'll notice, the sum of squared x's is a squared value, sum of squared y's is also a squared value. So those things are always positive. So the denominator of this R formula is always positive. The only thing that can ever be negative is the numerator, the sum of the xy's. And if you look at that formula for the sum of the xy's, it says x minus x bar times y minus y bar. Well, if you think about when that will be positive and when it will be negative, well, if you have a positive relationship, then that means it's increasing from left to right. So that means that small values of x occur with small values of y, and large values of x occur with large values of y. And when I say small values of x, I really mean values less than the mean. Large values of x means values bigger than the mean. So if you think about that, and you take a big value of x and a big value of y, and then you subtract the mean, assuming that big means bigger than the mean, then you're going to get a positive times a positive, which gives you a positive. If you take small values of x and y, that means a small value of x minus the mean will give you a negative. A small value of y minus the mean will also give you a negative. That gives you a negative times a negative, which is also positive. So the way you get a positive R value here is when small values of x and y occur together and large values of x and y occur together. The values in the middle occur together. And that, of course, is going to give you that positive slope. That's what a positive slope looks like, is it's basically increasing from left to right. The way you get a negative R is the opposite. The way you get a negative R is if small values of x occur with large values of y. So you get this inverse relationship. Because if small values of x occur with large values of y, a small value of x is going to give you a negative, a large value of y is going to give you a positive, and when you multiply those together, you get a negative. Same thing if you switch it around and you say large values of x and small values of y, you get a negative when you get this inverse relationship. So that sum of the xy's will be negative when the correlation is negative, and it will be positive when the correlation is positive. Now, I'm not going to have you explain that to me, but it is nice to just get some sense of what this formula is doing for you. And it's a very useful formula and a very common formula that we use in statistics. The one last thing, which takes a little bit of work, that I want to do with this R formula is this is not actually the version of the R formula that we're going to use to calculate R by hand. So we have some math to do in order to figure this out. We actually already simplified the sum of the squared x's back whenever we talked about variance, because that is the numerator of the variance formula. So let me run through that simplification first. If we take the sum of the squared x's and we just rewrite this sum, this is a common manipulation in statistics. If you want to rewrite this sum, we can square that out. If you square x minus x bar squared, if you square that out, you'll get x squared minus 2x bar x plus x bar squared. So you got to remember your properties of sums here. So what we can do is we can break that up and we can sum each part, and we get an expression that looks like this. Then what we can do is we can deal with constants, and we can actually pull the constants out front. So that first term is just going to be sum of x squared. Remember, x bar is now a constant because we've already calculated x bar. This is based on the fact that we know what the mean of the x's is. So 2x bar is just a constant. In that last quantity, x bar is just a constant. So when you sum a constant, you get n times the constant. So x bar squared is just a constant, so we get n times x bar squared. The next thing I do here is I just replace the x bars by what it is. Remember, x bar is the sum of x over n. So if we replace x bar by sum of x over n, we get an expression that looks like this. And then I just do a little simplification. So in that middle term, you can see there we have sum of x times sum of x. So that's sum of x quantity squared. Everything else stays the same. There's a 2 up front over n. In that last term, we actually have an n squared in the denominator. So actually that n out front cancels with one of those, and we just end up with sum of x quantity squared over n. The nice thing is now those last two terms are like terms. So we have minus 2 of those plus 1 of those. So we end up with a simplification, and this is a common simplification in statistics for our sum of squared x's. Is it really mathematically equivalent to the sum of x squared minus the sum of x quantity squared over n? So I just have it written out a little neater there at the bottom. This is a common simplification for sum of squared x. Those are the algebraic steps. Sum of squared y, of course, works exactly the same way, so I'm not going to do it twice. The only difference between sum of squared x and sum of squared y is in x you call the variable x, and y you call it y. So those are exactly the same algebraic steps, but this is the sum of squared x and the sum of squared y simplifications. So in order to get a computational formula for your R value, the first thing you need to do is just simplify these components. So we do have one other component to simplify, and that is the sum of the xy's. And we have not done this one before, so I will go through this one with you in a little more detail. So it does work in a similar way, and you'll see that the outcome is actually not that different than it is for the sum of squared x and sum of squared y. But we do have, in this case, the multiplication of x minus x bar times y minus y bar. So we have both an x and a y in this case. So the first thing we're going to do, of course, is FOIL this out. And when you FOIL out x minus x bar times y minus y bar, this is what you end up with. Then we're doing very similar steps. We're going to sum each part. So we sum each part. We just rewrite that as the sum of xy minus the sum y bar x minus the sum of x bar y plus the sum of x bar y bar. Okay, now we can deal with constants. And what you see when you do this for a while is you start to see that all these work in a very similar way. You always simplify, then you basically sum each part, then you deal with constants, and then you simplify again. And that's how you do all these. So we can pull out our constants here. So remember, y bar and x bar are constants. So in that second term, we pull out the y bar. In that third term, we pull out the x bar. And there at the end, x bar times y bar is just a constant. And remember, when we sum a constant, we end up with n times that constant. The next step is I'm just going to replace all those y bars and x bars with what they mean, so that we can actually simplify this thing algebraically, because we can't do much whenever everything's x bar and y bar, so we want to rewrite this in terms of x and y. So all I did there was replace everywhere there's an x bar, I replaced it by sum of x over n, and y bar works the same way, I replaced it by sum of y over n. So next what happens is you can just do a little algebraic simplification. So I just rewrote that second term there as sum of x times sum of y over n. I didn't really change anything. But the nice thing is it's now in the same form as that third term, which is also, you can see, just sum of x times sum of y over n. And then in that last term, you can see the n out front cancels with one of those n's. And the nice thing is here, you also end up with sum of x times sum of y over n. So basically what happens is those last terms just go away because you're subtracting and adding the same quantity. So you end up with a simplification here that is just sum of xy minus sum of x times sum of y divided by n. So here it is written out the same way as I did before. This is your simplification for sum of xy. So now that we have all three of those sum of squared terms simplified, we can manipulate R a little bit. So here I just have them all wrote out so that we can use them. This is our conceptual formula of our R value, which is the sum of xy over the square root of sum of squared x times sum of squared y. So all I'm going to do is just replace those sum of squareds by what we just simplified them to be. And when I do, it looks a little messy, but this is what I end up with. So we're almost done. This is very close to the computational formula we use for R. We don't like to use just sum of squared x's. Same thing with variance, because it's got that x bar in it. And when you have a decimal there and you round it, then you end up just compounding your rounding error, because you're going to take every x, subtract this value that you rounded, then you're going to square it, which compounds your rounding error, and you're going to end up with a bunch of rounding error if you try to do this using the sum of squared x, sum of squared y, and sum of the xy. So it's much better to use the simplification and come up with an easier formula to use. So we're very close here, but the thing we don't like about the formula the way it is the fact that we have a complex fraction. We don't like having, within the numerator, for example, we have a fraction that has an n in the denominator. And you can see the same thing in the bottom of this fraction under the square root. So we need to get rid of those n's in the denominator. So the way to do this is just to multiply this whole thing by n over n. If we multiply by n over n, we're multiplying by 1, so we're not changing anything. And if you do this, things work out really nice and neat. Because when you distribute the n in the numerator, we just get n times the sum of the xy's. And in that second term, the n's cancel. So you just get minus sum of x times sum of y. And then in the denominator, well, we have this square root. So it works out really nice, because if we move n inside of the square root, then n basically becomes n squared, because the square root of n squared is n. So that means whenever we move this inside of the square root, we basically have two n's, because we have n squared. So we can distribute one of those n's through that first parenthesis, distribute the other n through the second parenthesis, and that will allow us to get rid of those n's in the denominator there within those two parentheses under the square root. And that will give us this formula you see here at the bottom. And this is the formula that you should use when you calculate R by hand. It looks kind of messy. It's more tedious than difficult. You do have to be careful when you calculate R. Try not to make any simple mistakes, but it's really not that bad to calculate R. And I'm going to give you an example here in a few minutes in terms of using this formula to calculate an R value. Before we do that, though, let's go ahead and talk a little bit about the mathematics that goes along with linear regression. So once we establish a strong correlation, we look at the scatter plot, we have a strong R value. Once we do that, then we're going to be able to say that this relationship is strong enough to predict our Y variable based on our X variable with a small amount of error. So we're going to create a linear model that expresses Y as a function of X, plus we're going to have random error within this model. Now, when you actually see the equation, you're not going to see any error involved, but technically there's error included because all the points do not perfectly, the line does not perfectly go through all the points. So there is error included in this model. That's always the case. So the general form of our equation, it's basically a linear equation like y equals mx plus b. In statistics, we actually write it as y equals beta naught plus beta 1x. Beta 1, of course, is your coefficient for x, so that is your slope. Beta naught is your y-intercept. So in your mx plus b, basically, we call m beta 1, we call b beta naught. In statistics, there's some reasoning behind why we do that, but I'm not going to go into that during this lecture. But that's the way that you will see linear equations written. So to calculate the linear equation, to figure out what the linear equation is once you've established a strong relationship, we basically need to figure out what beta 1 and beta naught is. And the big one, of course, is beta 1. Beta 1 is basically calculated, it's the slope. And the way we calculate slope is we basically take rise over run. In general, that's what it represents. We need the slope of this line. Well, if you work through that and you figure it out, basically the way it works out to be is it works out to be the sum of x, y over the sum of squared x's. And basically what that is going to end up telling you is how much y changes for each unit change in x, which is why your denominator includes the x. And then whenever we include a numerator of sum of the xy's, we end up with basically a value that represents for every unit change in x, how much is y going to increase? That's what the slope represents in a linear equation. So all I did here was exactly what we did on the previous slide with r. We just replaced the sum of xy and the sum of the squared x's with their definition. And then if you algebraically plug in what we did before, or what we simplified those sum of squareds to be, and then you multiply by n over n, you'll get this equation to the right. I don't feel any need to show you that again because it's very similar to what we did with r. I'm sure you could figure that out on your own. But basically just a simple algebraic manipulation here, because we've already done most of the hard work with simplification of sum of squares. You can get this formula to the right, which is the formula that you're going to use for beta 1. I'll show you later on how this is really easy to calculate if you've already calculated r, because notice that these quantities that you see in this beta 1 formula are also quantities included in the r formula. So once you calculate r, you can actually just pull off a couple quantities from the r formula and use it to calculate beta 1. So once you get your slope, the other thing that we know is the best fit line is always going to go through the point x bar comma y bar, where x bar is the mean of your x values, y bar is the mean of your y values. So basically, if we have the slope and we have a point, which is x bar comma y bar, then we can figure out what the y-intercept is going to be. You did that in algebra class. So basically, beta naught is just y bar minus beta 1 x bar, and that's nothing more than having a point in the slope and figuring out what the y-intercept is going to be. Now, if you replace this and do it using the quantities we're going to have available to us, then it's much easier to do it using this last formula that I have here, which is nothing more than just replacing y bar by sum of y over n and replacing x bar by sum of x over n. You end up with this formula you see over here to the right behind beta naught, and that's the easier formula to use based on the information you're going to have when you do these kinds of problems. So that's the formula you should use for beta naught. Okay, so now we've went through kind of all the conceptual stuff, talked about the algebra, talked about the fact that we need correlation in order to use regression. Now let's just actually do an example so you can see how this works. So here's the example we're going to use. Suppose we are interested in the relationship between how many cups of coffee a person drinks and how many hours they sleep at night. We want to predict hours of sleep based on number of cups of coffee. Okay. So the first thing we need is some data. So of course you're going to be given the data, and suppose your data set looks like this. We have our x and we have our y. So x just represents how many cups of coffee a person drinks, and then y represents how many hours that person slept that night. So the first thing we're going to do is we have to establish All right, well, are these two things correlated? Do we have a strong relationship? And if we do have a strong relationship, then we can do what we want to do here. We can predict how many hours of sleep they're going to get based on how many cups of coffee they drink. So to look at the relationship, the first thing we're going to do is create a scatter plot. I went ahead and created a scatter plot that also fit a line to the points, but here is the scatter plot it's actually called a fitted line plot, where the points or a line is actually fit to those points using the method of least squares. And you can see that all the points are really close to the line here. You can also see that this line has a negative slope, so we would expect this to be a strong negative linear correlation. The big thing that you look for in the scatter plot is make sure there's no extreme values. You don't want any values that are really separated from the rest of the values that are making all the other values look like they're close together. Like, you don't want a really high x value and then all the other x values to be really small, for example. That will overinflate your R and make it look like it's a strong relationship when it's not. But here, everything looks good. There's no extremes. All the points generally follow a line with a negative slope. So it looks like we're going to be able to establish a strong relationship here and be able to get a good R value. You look at your scatter plot and you calculate R in order to establish a strong relationship. So the scatter plot looks good here. So now to get R. Well, to get R, we need to use that R formula. It's kind of messy that I just showed you. So it's always the same quantities that you need for R. You basically need the sample size N, which that's simple here. It's just how many points we have. We have 7 data points here, so N is 7. But you also need 5 different sums, and it's always the same 5. So you need to sum the x values. That's simple. That's just the sum of that column of x values. You need the sum of your y values. That's also just the sum of that y column. But then you also need the sum of your x squareds. You need the sum of your y squareds and the sum of your xy's. So the best way to do this is just to create columns. And we did this before whenever we dealt with sums. But let me just show you what it's going to look like whenever you do it for this example. So we always have these same 5 columns. X and Y are our data. They're going to be given to us. But we also need to create a column of x squared because we're going to need the sum of our x squareds. We need a column of y squareds and a column of xy. So to get the column of x squareds, we simply just square our x values. To get the column of y squareds, we simply just square our y values. To get the xy values, that means x times y. So for example, across that first data point, we get 4 times 7, which is 28. The second data point is 7 times 5, which is 35. So that last column is our x value times our y value. So we just create this table. And then once we create this table, we figure out what the sum of each column is, and that gives us the sums that we need. You can see at the top there, I also identified the sample size because we also need N. N is 7. There are 7 data points. So the quantities we need is N is 7. We know in this case the sum of x is 33. That's the sum of my x values. The sum of my y values is 45. The sum of my x squareds is 209. The sum of my y squareds is 313. And the sum of the xy's is 177. So once I have that information, always do this first when you calculate R. Create this table, get these sums that you need. Once I have that, then I can think about calculating R. So in order to give myself some space here, I just kept what we need. We really need those sums along with our sample size. So now we're ready to calculate R. So here's our R formula. And it looks kind of messy, but if you break it down into parts, it's really not that bad. Because now we know everything we need for this equation. So if we start plugging stuff in, you can see across the top there in the numerator. For N, we plug in our sample size of 7. The sum of the xy's we plug in. The sum of the xy's is 177. The sum of the x's is 33. The sum of the y's is 45. So it's really just a matter of plugging the proper quantities in. If you look at your denominator under that square root, in that first parenthesis, again the sample size is 7. The sum of the x squareds is 209. And then the sum of the x's is 33. And of course, we're going to square that quantity. If you look in the second parenthesis, again, the sample size is 7. The sum of the y squareds is 313. And then, of course, the sum of the y's is 45. Now it's just a matter of really solving this thing. And when you solve it, I recommend you do this in 3 parts because it is kind of messy to try to put this whole thing. Please don't try to put this whole thing in your calculator. That would be a mess. So do it in 3 parts, and you end up with a pretty simple expression that looks something like this. So do the numerator. The numerator is just that 7 times 177 minus 33 times 45. If you do that here, you get negative 246. And then break up your denominator into 2 parts because you have those 2 parentheses down there. So that first parenthesis is 7 times 209 minus 33 squared. If you work that out, you'll get 374. The second parenthesis is 7 times 313 minus 45 squared. That will give you 166. And now we have something that's pretty straightforward to work with. If you crank through the math there, you will get an R value here, a very strong R value of negative 0.987. It's what we expected. It's got a negative relationship. And we know that the points are all very close to the line. This is very close to negative 1. So we have a strong negative linear relationship here. Strong negative linear correlation. So that's R. That's how you calculate it. Remember, R always has to be between negative 1 and 1, and you got to be able to interpret that R when you get it. It's also nice if you see the scatter plot because these two things should correspond to each other. I mean, the R value is measuring how close the points are to the line. So you should see that also when you look at the scatter plot to see if your R value is reasonable. Now that we have our R, we've established that the scatter plot looks good. Everything looks good here. So now we're able to say, well, since I have this strong relationship, let's predict. Let's predict how much sleep someone gets based on how many cups of coffee they drink. So we're going to identify the regression equation. So to identify the regression equation, you always start with the slope. That's what you want to start with in terms of your calculations. So there's something very important to notice here. If you compare the numerator of beta 1 to the numerator of R, you will see that they are exactly the same. This is actually the reason why your R value is always the same sign as beta 1. R and beta 1 will always have the same sign. Remember, we said if R is positive, it means you have a positive slope. The reason being is because both of these quantities, the sign is determined by the same numerator. So it's got to be the same. So the numerator of beta 1 is just the same as the numerator of R. The denominator of beta 1 is actually the same as that first parenthesis under the square root. It's that n times sum of x squared minus sum of x quantity squared. So we actually have that denominator just in that first parenthesis under that square root in your R formula. So all you have to do to calculate beta 1, once you've done the hard work of calculating R, is just pick those two quantities off because we know the numerator of R is negative 246. We already solved that. We also know that first parenthesis when we calculated R was 374. That means our slope here, all you have to do is take negative 246 divided by 374, and that will give you your slope, which is negative 0.658. So to give ourselves some more room, I'm going to move that up to the top. So now we have our slope. Once you have your slope, then you can figure out your y-intercept. So your y-intercept, as we mentioned before, you use the sum of y minus beta 1, sum of x all over n formula. So now we just plug in what we know. We know the sum of the y's is 45. Our slope, we just figured that out to be negative 0.658. The sum of x is 33. And then, of course, our sample size is 7. If you work through this, you'll get an intercept of 9.529. We can then create our formula. All regression formulas use the same form, y equals beta naught plus beta 1x. So we simply just plug in beta naught and beta 1. So we know beta naught is 9.529. We know beta 1 is negative 0.658. So we end up with a regression equation that is simply 9.529 minus 0.658x. This is our best fit line using the method of least squares for this set of data. That's how you come up with your regression equation. So it's very important you're able to do this. It's very important you're able to calculate an R value. It's very important you're able to come up with your regression equation from a set of data points. You got to be able to do this. Once we have our regression equation, so the whole point of getting this regression equation, well, one of the main points of getting this regression equation is so that we can start to predict y based on x. So now we can answer a question like this. Let's predict how many hours of sleep we would expect someone to get with 6 cups of coffee. So we already said our regression equation, this is the same equation that we just figured out, is y equals 9.529 minus 0.658x. So to predict, it's simple. Once you come up with a good model, it's really simple to predict. We just plug in 6 for x. That will allow us to predict y. So for 6 cups of coffee, we would predict 5.581 hours of sleep. It's really that simple. So the prediction part is simple once you come up with the model. The hard part is getting the model, and first, of course, establishing that it's a good model by looking at your R value and looking at your scatter plot. Another thing that's important to mention here is I do want to mention this issue, and this is one of the mistakes that you'll see with regression sometimes. So I asked this question: should you use this model to predict hours of sleep with 20 cups of coffee? And the answer to that is no, you shouldn't. And if you would go back and look at our original data, what you'll find that for cups of coffee in our data set only went from 1 cup to 10 cups. So this is outside the range of our data. That's called extrapolation, and you should not use regression to extrapolate. So we only know that this relationship holds between 1 and 10 cups of coffee. We don't know what happens outside of that. We actually would know if we actually plug in 20 into this equation, you will actually get a negative value. You will actually get negative 3.631. So we know that can't even be right. We cannot sleep a negative number of hours during the night. So our y value cannot be negative here, so we know we can't plug 20 into this model. And the reason why that happens is because this model only works between 1 and 10, which is the range of our data. So it only works if we do what we call interpolation, which is what regression is designed for. It's designed to predict within the range of our original data, not to extrapolate outside of that range. One other thing we want to mention, and that is the idea of a residual. So I've talked a little bit about error in the model. If you really look at the mathematics behind this, sometimes you'll see this formula written as y equals beta naught plus beta 1x plus e. And e represents how much error you have, or basically the distance between each point and the line. And every data point has some distance between the point and the line. If it's actually on the line, that distance is 0. If it's below the line, that distance is negative. If it's above the line, that distance is positive. But that distance is actually what we call, for the original data, is actually what we call the residual values. The residual values are just the difference between the actual value and the predicted value. We call these our e's. They're a measure of error. So every data point has what we call a residual. Like I said, this is a measure of error. And if you ever take any more advanced statistics courses, this is one of the next common steps that you would do with regression, is start to really look at these residual values, because they should have certain characteristics within a good model. So we won't get too much into that during this course, but it is something that you look at lots of times in more advanced courses. So we're going to find the residual for the point 3, 7. And all you have to do to find the residual is you basically take the actual y value, which is 7 in this case, because the point's 3, 7, and we subtract out what the predicted value would be. So the predicted value would be whatever it is whenever I plug 3 into the equation. That would give me a predicted value. So this is how we write the residual equation. It's probably easiest to just use this equation, but it's basically what I said. You take the actual y value, and then you subtract out what you get whenever you plug in x into the regression equation. So if we do it in this case, the regression equation, so this next step really just writes out the regression equation. So we know our regression equation in this case, beta naught is 9.529, beta 1 is negative 0.68. So we just plug those in and we get a residual equation that looks like this. And then if we actually work this out, then we get 7 for our y value. Our predicted y value, when you plug in 3 into this equation, will work out to be 7.555. So when we subtract this, we get a negative residual here, which is negative 0.555. So that negative residual tells us that this is actually below the regression line. If that was positive, it would be above the regression line. And if you actually add up all the e values, they'll actually add up to be 0 because of the way we pick the line. Because the points above and below the line balance out. And if you add up all the residuals, if you calculate them for every point, they'll actually just sum to be equal to 0. That is a property that sometimes people will mention with residuals. We won't go into that too much, but The residuals is really a good measure of error because it tells you how far these data points that you use to create the line, how far they actually are away from the line. So it's important you're able to calculate a residual value. So that's what we cover here. We cover this idea of correlation with scatter plot and with an R value, and then the idea of regression. You got to be able to calculate the regression equation, use it to predict, calculate the residuals, and understand the basic principles and ideas behind correlation and regression. That is it for section 10.